It was November 12, 1942, when the SS Robert E. Peary slipped into San Francisco Bay. The moment marked something extraordinary. A fully functional cargo vessel had traveled from her initial keel laying to completion in just 4 days, 15 hours, and 29 minutes. The ship herself was impressive by any standard. At 441 feet long and weighing 10,500 tons, she represented a feat most people couldn't fathom. Traditional shipbuilding took 7 months or more. Kaiser's approach had compressed that timeline into what most people might spend on a vacation. The Navy establishment viewed Henry J. Kaiser with deep suspicion. He wasn't a lifelong maritime man. He'd built dams, concrete structures, roads, never a ship before in his career. Yet here he stood, about to revolutionize an entire industry that had operated unchanged for 2,000 years. Across the country, traditional shipbuilders dismissed his theories as amateur fantasies. They'd mastered their craft through generations of careful, methodical work. Ships weren't products to manufacture like automobiles. They were vessels requiring artisan skill, time-honored techniques, reverent construction practices. But Kaiser saw something different entirely. He recognized that ships were indeed products, and products could be manufactured efficiently. The stakes pushing this unconventional thinking couldn't have been higher. German U-boats were hunting Allied cargo ships across the Atlantic with devastating success. Britain faced starvation as supplies dwindled. America needed thousands of cargo vessels to transport 2 million troops across 2 separate oceans. The conventional approach would require 10 to 12 months per ship. At that pace, the war would conclude before sufficient vessels could be built. For 20 centuries, shipbuilding had followed an unvarying formula. Craftsmen worked upward from the keel, riveting steel plates one by one in a painstaking ascent. Training a skilled riveter consumed 6 months. The process demanded tremendous patience and expertise. Kaiser understood that America simply didn't possess this kind of time. His insight was deceptively simple. Welding could be taught in just 10 days. One welder could accomplish what 2 riveters required. The methodology was radical enough, but Kaiser's hiring practices shocked the maritime world even more. His shipyards opened their doors to women, to wounded veterans missing limbs, to disabled workers, to African Americans systematically locked out of skilled trades by union restrictions and prejudice. Performance mattered more than pedigree. The Navy issued stern warnings. Welding ships was dangerous, they insisted. The steel hadn't been designed for fusion at such temperatures. Brittle fracture could develop, catastrophic failures could occur, people could die. But Kaiser grasped something the experts refused to acknowledge: that America's riskiest manufacturing approach had become the nation's only viable path to victory. When Admiral Emeryland received the telegraph from Richmond Shipyard No. 3 that morning, the numbers seemed impossible. 4 days, 15 hours, 29 minutes. A fully operational cargo vessel capable of transporting 2,800 jeeps or 440 tanks had entered San Francisco Bay faster than most naval bureaucrats could process a single purchase order. He stared at the message, then at the stack of traditional shipbuilding contracts covering his desk. 230 days represented peacetime standards. Even the British, desperate and innovative, required 70 days minimum. Kaiser had shattered the conventional understanding of what ships could achieve. Henry J. Kaiser walked across the muddy grounds of his Richmond shipyard, his expensive suit already bearing traces of welding sparks and California dust. At 60 years old, he moved with the restless energy of someone who'd transformed the impossible into routine throughout his career. The Hoover Dam, the Bay Bridge, the Grand Coulee, projects engineers said couldn't be built, completed ahead of schedule and under budget. Ships presented a different challenge entirely. Ships carried human beings across vast oceans where mistakes meant drowning in darkness. The established shipbuilders reminded him constantly, their voices dripping with condescension reserved for outsiders who didn't grasp maritime tradition. But the SS Star of Oregon had provided his first genuine proof of concept, launched in September 1941 after merely 131 days. That was 100 days faster than industry standards. The maritime establishment had dismissed it as beginner's luck, a fluke that would never repeat itself. They'd been constructing ships the same way since Phoenician times: keel first, ribs next, plates riveted methodically one by one in that ancient vertical climb. Kaiser's revolution hadn't emerged from maritime expertise. It came from manufacturing logic learned through concrete and steel. While traditional shipbuilders thought vertically from keel to superstructure, Kaiser envisioned horizontal assembly lines where standardized sections could be prefabricated simultaneously across the country. 250,000 parts manufactured in factories from coast to coast, then transported to shipyards as massive 250-ton modules. Like assembling enormous steel Lego pieces, each component designed to fit perfectly with its neighbors. The welding gamble represented Kaiser's boldest departure from tradition. For 2,000 years, ships had been riveted. Steel plates overlapped and fastened with heated pins hammered through both surfaces, then pounded flat on the opposite side. The process proved labor-intensive, requiring teams of skilled workers while creating thousands of potential leak points. Welding fused metal directly into continuous seams, stronger than the plates themselves. Crucially, welders could be trained in 10 days versus the 6 months riveters demanded. One welder could do the work of 2 riveting teams. The mathematics proved undeniable, though mathematics had never sailed through a North Atlantic tempest. Kaiser's workforce transformation proved as revolutionary as his technical methods. As men were drafted faster than shipyards could replace them, Kaiser hired those considered unemployable. Women who'd never touched industrial equipment, wounded veterans, disabled workers dismissed elsewhere, and African Americans barred from skilled trades by union prejudice. His shipyards became accidental laboratories of American democracy, where performance mattered more than background. Each worker mastered one specific task, achieving precision through repetition rather than years of apprenticeship. Production lines hummed with voices speaking dozens of languages, united by common purpose. The established shipbuilding industry watched Kaiser's early triumphs with mounting alarm. Their warnings about welded construction carried the weight of centuries. Riveted joints had built every great navy in history. When plates cracked in riveted construction, the damage stayed contained. Fractures would stop at the joints between overlapping sections. Welded holes created continuous metal surfaces where cracks could race unimpeded from bow to stern. The steel itself hadn't been formulated for welding. The chemistry developed for riveted construction might behave unpredictably when fused at 2,000 degrees. By early 1943, Kaiser had reduced construction time from 940,000 labor hours per ship to 352,000 hours. His average completion time had dropped to 70 days, then 50, then an almost unbelievable 39 days. The Joseph and Teal had astonished observers by launching after just 10 days of assembly. But the Robert E. Peary represented something beyond mere velocity. It proved that American industrial capacity could rewrite fundamental manufacturing laws when survival demanded impossible performance. The implications extended far beyond individual vessels. German U-boats were sinking Allied ships faster than traditional yards could replace them. Britain's Atlantic lifeline was severing, one cargo at a time. At conventional production rates, the war would end before America could build sufficient merchant marine capacity to supply 2 million troops fighting across 2 continents. Kaiser's assembly line approach offered the only mathematical solution to an existential crisis. Build ships faster than enemies could sink them, or watch democracy drown in the Atlantic. Kaiser stood on the launching platform as the Robert E. Peary's hull touched water for the first time. Her well-welded seams gleamed in the California sunshine. Behind him, cranes were already positioning keel plates for the next vessel. The production line never paused. Traditional shipbuilders called his methods reckless, dangerous, unprecedented. They were absolutely right. But precedent had become a luxury America could no longer afford. 3,000 miles eastward, at Todd Shipyards in Brooklyn, workers swarmed over a skeletal hull in that winter of 1942. Riveting teams hammered steel plates one by one in the methodical climb from keel to deck that had defined shipbuilding for 20 centuries. The rhythmic percussion of pneumatic hammers echoed across the East River as riveters drove heated pins through overlapping steel plates, flattening the protruding ends with practiced skill. 6 men per team. Heater, catcher, bucker, riveter, each requiring 6 months of training. The hull would consume 8 months to complete, assuming no delays for weather, material shortages, or the inevitable injuries plaguing industrial construction. 3,000 miles west, Henry Kaiser's Richmond shipyard operated under entirely different principles. Instead of thinking vertically from keel upward, Kaiser had reimagined ship construction horizontally. Massive prefabricated sections were built simultaneously in factories across America, then transported by rail for final assembly. The bow section arrived from a steel mill in Pennsylvania. Engine mounts were fabricated in Detroit using automotive assembly techniques. Superstructure components rolled off production lines in Seattle, each piece tagged with numbers corresponding to precise positions in the final vessel. The approach violated every sacred tradition of maritime construction, which was exactly why it worked. Kaiser's most radical innovation wasn't organizational but metallurgical. Welding had existed for decades as a repair technique, used sparingly to patch damaged plates or seal minor leaks. Kaiser proposed something different entirely, fusing entire hulls with continuous welded seams, eliminating the overlapping plates and thousands of rivets traditional construction required. The implications were staggering. Welded ships used significantly less steel because plates didn't need overlap. They moved faster through water because rivet heads no longer projected into the flow, creating resistance. The welding revolution transformed everything about how ships could be built. Where riveting demanded half a year of specialized training, welders mastered their craft in just 10 days. One experienced welder could accomplish what previously required 2 entire teams of riveters working in concert. The mathematics worked powerfully in Kaiser's favor. Traditional shipbuilding required armies of highly trained craftspeople who had spent years perfecting their trade through long apprenticeships. Precisely the kind of skilled workers the military was drafting away faster than shipyards could train replacements. Kaiser's revolutionary approach changed the equation entirely. Instead of needing workers with deep maritime knowledge, he could teach people to master single-focused tasks through repetition. An Oklahoma housewife learned to weld superstructure joints in a single week. A wounded veteran who'd lost his left arm could operate overhead cranes with mechanical precision. Disabled workers whom other employers had dismissed discovered meaningful employment in Kaiser's assembly lines. When jobs were designed around what people could actually do, rather than what tradition said they should do, their supposed limitations simply vanished. The transformation at Richmond Shipyard shattered every rule of American industrial employment. Women represented nearly 30% of Kaiser's workforce by early 1943, many earning steady industrial wages for the very first time in their lives. African Americans secured skilled positions that unions had previously blocked them from entering. Their welding torches burned just as bright as anyone else's. Missing limbs, accented English, young teenagers too fresh-faced for military service, none of it mattered. Kaiser's yards became unintentional laboratories where actual capability counted for more than family background or how someone looked. The technical genius lay deeper still. Each Liberty ship contained exactly 250,000 individual components, from massive engine blocks down to the tiniest electrical fittings. Every single part had to connect perfectly with its partner, regardless of which factory had manufactured it or which coast it had traveled from. Kaiser borrowed automotive manufacturing's approach to tolerances and quality control, creating the first truly interchangeable ships in maritime history. A rudder forged in Baltimore would fit perfectly onto a hull assembled in California. Engine parts from Detroit worked flawlessly with transmissions from Chicago. Standardization meant damaged Liberty ships could be repaired at any Allied port using replacement components manufactured anywhere across America. But the welding transformation exposed something shipbuilders had never fully confronted. Riveted construction had actually hidden fundamental flaws in steel for centuries. Plates fastened mechanically left overlapping sections containing hidden cracks along the joints. Welding subjected steel to temperatures exceeding 2,000 degrees Fahrenheit, fundamentally altering molecular structure in ways maritime engineers scarcely understood. The fused seams created continuous metal surfaces where stress distributed more evenly, but also where cracks could tear through unimpeded if the base material proved inadequate. Kaiser was essentially betting America's merchant marine on metallurgical science that shipbuilders had never tested at this scale. Kaiser's quality control resembled automotive production far more than traditional shipbuilding practices. Every welded seam underwent X-ray inspection to catch internal flaws invisible to the naked eye. Workers rotated between stations to prevent fatigue from causing mistakes. Prefabricated sections arrived with detailed inspection certificates documenting every measurement and material specification. This systematic approach eliminated the craftsmanship variables that made traditional ships unique, and sometimes catastrophically flawed. Every Liberty ship would be essentially identical, built to such precise specifications that parts became genuinely interchangeable between vessels. The production acceleration bordered on the miraculous. Where conventional yards completed perhaps 4 ships annually, Kaiser's Richmond facility was launching vessels weekly by summer 1943. Prefabrication networks spanning the continent meant multiple ships could be under construction simultaneously. Bow sections formed in Pennsylvania, while engine mounts were machined in Michigan and superstructures took shape in Washington. When components converged at final assembly, construction became choreographed connection rather than laborious fabrication from raw materials. The established shipbuilding industry watched with growing horror disguised as professional skepticism. This wasn't merely faster construction, it fundamentally challenged maritime expertises accumulated across millennia. Welded seams had never been tested through North Atlantic storms. Modular construction eliminated the subtle adjustments that master shipwrights made during traditional assembly. The workforce lacked generational knowledge about how ships behaved in heavy seas. Kaiser was conducting the largest metallurgical experiment in history, using vessels carrying American lives across submarine-infested oceans, and honestly, nobody was certain whether welded hulls would actually hold together when it truly mattered. By spring 1943, the competition between Kaiser's shipyards became a spectacle drawing reporters nationwide. Richmond Shipyard No. 3 shattered its own records so frequently that construction times seemed to exist in freefall. Each launch ceremony celebrated achievements that would have seemed impossible mere months before. The first Liberty ship required 124 days from keel to launch. By summer, Kaiser's average had plummeted to 39 days. Then Oregon Shipbuilding Corporation in Portland completed the Joseph N. Teal in just 10 days, an accomplishment so extraordinary that Navy inspectors initially refused to accept the documentation. Kaiser's response proved characteristically audacious. He would build a ship in less than a week. The SS Robert E. Perry became his ultimate proof of concept, a vessel whose construction timeline seemed to violate the fundamental laws of industrial manufacturing. Assembly commenced on Sunday, November 8, 1942, as prefabricated sections converged on Richmond from across the continent. The bow section had been welded in Pennsylvania. Engine mounts arrived from Detroit aboard specially designed railroad cars. Superstructure components rolled into the yard from Seattle, each piece tagged with numbers indicating its precise position in the finished vessel. By Thursday evening on November 12th, the completed ship slid down the ways into San Francisco Bay. 4 days, 15 hours, and 29 minutes after the first keel plate was positioned. The achievement transcended mere speed. It represented industrial choreography, executed with supernatural precision. By 1944, Kaiser and his competitors were launching 50 merchant vessels daily, more ships than the entire American maritime industry produced annually during peacetime. Nearly 1,500 vessels rolled down Kaiser's ways alone, representing 27% of all U.S. Maritime Commission construction throughout the war. Each ship carried the industrial DNA of an entire continent: steel from Pennsylvania, engines from Michigan, electronics from Massachusetts, lumber from Oregon, assembled by workers who 18 months earlier had never touched a welding torch or operated a crane. Richmond transformed from a quiet Northern California town into a bustling industrial metropolis almost overnight. Population exploded from 20,000 to over 100,000 as workers poured in from across America. drawn by wages higher than anything available back home. Kaiser's yards hummed around the clock with 3 shifts covering every single hour. Welding sparks visible from San Francisco, 20 miles away, painted the night sky orange. The shipyards became cities unto themselves, complete with medical clinics, childcare centers, and housing developments constructed as rapidly as the ships themselves. Workers who'd never earned more than subsistence wages suddenly received steady paychecks, plus employer-provided healthcare through Kaiser's pioneering prepaid medical program. Women comprised nearly 30% of his workforce by 1943, many working industrial jobs for the first time while their husbands served overseas. African Americans secured skilled positions previously barred by union discrimination. Their welding certifications carried equal authority with any worker's credentials. Wounded veterans discovered missing limbs didn't prevent them from operating cranes or managing prefabrication schedules. The shipyards became accidental laboratories where American equality actually worked, where performance mattered more than prejudice and genuine capability counted for more than convention. Kaiser's competitive advantage extended far beyond speed into cost efficiency that revolutionized maritime economics. His ships were completed in 2/3 the time, at 1/4 the cost of traditional shipyards, margins that rendered conventional construction methods obsolete. The secret rested in standardization and mass production techniques borrowed from automotive manufacturing, identical components produced simultaneously across the continent, then assembled with mathematical precision at final construction sites. Labor costs plummeted when workers mastered single tasks rather than comprehensive maritime skills. Material waste disappeared when every plate and beam was cut to exact specifications before reaching the shipyard. The catchphrase captured both urgency and audacity. Build ships quicker than the Japanese can sink them. German U-boats were destroying Allied merchant vessels faster than traditional yards could replace them, creating a race between American industrial capacity and enemy naval power. Each day's delay meant additional cargo ships resting on ocean floors, their crews dead and supplies feeding fish instead of reaching Allied armies. Kaiser's assembly lines represented America's industrial immune system, generating replacements faster than enemies could destroy them. The mathematics were stark and simple: produce or perish. Yet enormous technical risks lurked beneath the celebration surrounding each launch. No one had tested Liberty ship construction techniques through North Atlantic storms. The continuous welded seams enabling rapid assembly created potential failure points unknown in riveted construction. Steel chemistry optimized for mechanical joining might behave unpredictably when fused at welding temperatures. Kaiser was conducting the largest metallurgical experiment in maritime history, using vessels carrying American lives through submarine-infested waters. Every launch represented a bet that American industrial innovation could overcome centuries of maritime tradition. Production efficiency reached levels seeming to violate physical laws by late 1943. Kaiser's yards were launching completed vessels faster than some traditional facilities could install engines. The Joseph N. Teal's 10-day construction meant every component, from massive propeller shafts to tiny electrical fittings, had been manufactured, transported, and installed with approaching perfect precision. Any delay, misfit, or quality problem would have extended construction time catastrophically. The achievement required coordination between hundreds of suppliers across the continent, each delivering components that had to mate perfectly with parts manufactured thousands of miles away. The impossible had become routine at Kaiser's shipyards, where daily launches created a rhythm of industrial achievement, redefining American manufacturing capability. Workers arrived each morning knowing they would complete tasks considered impossible mere months earlier. Welders fused seams with precision exceeding traditional riveting. Crane operators positioned 250-ton sections with tolerances measured in inches. The assembly lines hummed with the confidence of people discovering they could accomplish absolutely anything when survival demanded excellence. Kaiser hadn't merely revolutionized shipbuilding, he'd shown that when necessity strips away the comfort of doing things the way they'd always been done, American industrial might could rise to meet absolutely anything. On November 14, 1943, at 3:17 in the morning, Coast Guard headquarters received a radio message from the SS John P. Gaines that would change everything. The words crackled through their receivers, urgent and terrifying. Ship breaking up, hull fracturing, 10 men lost, vessel abandoned. Within hours, more distress calls poured across the Atlantic as Liberty ships began experiencing catastrophic failures nobody had anticipated. These weren't minor structural problems. They were complete breakdowns of everything naval architects thought they understood about how ships held together. The SS Schenectady provided the most devastating example. A crack split down both sides of her hull toward the keel with shocking explosive violence. Her midsection rose upward as both the bow and stern plunged into the black, freezing Atlantic. The welded seams that had made Kaiser's production miracle possible were tearing apart like paper, and sailors were dying. As winter 1943 turned brutal, reports flooded into Washington showing the full scope of the nightmare. More than 1,000 ships developed cracks. Some were small surface fractures, harmless enough. But 190 vessels suffered serious damage that made them unseaworthy. A dozen broke completely in half, leaving their crews with impossible choices between climbing into lifeboats or going down with the ship. The numbers told a horrifying story. For every 100 ship years of service, welded vessels suffered 4.3 serious fractures, compared to just 1 per 100 for traditional riveted ships. Kaiser's revolutionary methods weren't simply failing, they were executing sailors with mechanical ruthlessness. An investigation launched in April 1943 exposed the metallurgical disasters hidden inside Kaiser's hulls. Secretary of the Navy Frank Knox assembled a board to examine how these welded steel vessels had been designed and built, a formal response to an engineering catastrophe eating through $50 million and irreplaceable lives. British metallurgist Constance Tipper became the investigation's most important voice. Her expertise in crystallography gave her the ability to examine broken steel like a detective studying crime scenes. What she found shattered centuries of assumptions about how steel behaves. The problem was the steel itself. Its chemical makeup had been optimized for riveted construction, where bolts and rivets contained any spreading cracks. Sulfur levels were far too high. Manganese was dangerously low. This created internal weaknesses that became catastrophic when exposed to welding temperatures above 2,000 degrees. The molecular structure worked fine when plates were bolted together. But when the welding torch fused metal, everything changed. Welders trained in just 10 days rather than 6-month apprenticeships created tiny faults in the seams, microscopic imperfections that could trigger fractures under pressure. Continuous welded hulls created a straight path for cracks to race from one end of the ship to the other with nothing stopping them. But the real enemy was the cold itself. North Atlantic water transformed steel from something that bent into something that shattered like glass through what scientists called ductile to brittle transition. Steel that flexed under stress in warm water turned brittle and explosive when temperatures dropped below critical levels. Riveted construction had hidden this for generations because fractures stopped at the overlapping plate joints. Welded hulls erased those natural barriers, creating open highways where cracks could sprint unchecked. Square corners, designed because they were easy to manufacture, became stress concentrators that started failures. Inadequate understanding of fatigue meant ships were breaking under stresses their designers never imagined possible. Throughout that brutal winter, the toll climbed as more vessels fell victim to structural failures that seemed to follow no logical pattern. Some ships snapped apart while sitting motionless at anchor in calm water. Others survived Atlantic gales only to fracture while being loaded in protected harbors. The SS Pendleton split completely off Cape Cod, sparking one of the most perilous Coast Guard rescues in maritime history. Captains reported hearing ominous groans from the hull as tension mounted. The steel itself was crying out warnings that welded construction had exposed flaws buried for centuries. Insurance companies stopped covering welded ships. Merchant sailors demanded hazard pay, treating these vessels as floating coffins. Kaiser faced a crisis that threatened his reputation and seemed to prove every skeptic who'd warned against his radical methods. The man who'd built Hoover Dam and transformed American construction suddenly stood accused of killing sailors through reckless experiments with untested techniques. Labor unions demanded an immediate halt to welded ship production. Navy officials questioned whether speed was worth lives lost. The industrial marvel that had let America build ships faster than enemies could sink them was killing more sailors than German torpedoes. The real answers surfaced slowly as metallurgists like Tipper dissected failed hulls with scientific precision that resembled forensic work. The issue wasn't welding itself, but the collision of poor steel chemistry, inadequate quality checks, and environmental stresses traditional construction had never faced directly. Untrained welders created hidden defects in the seams. Flawed steel composition made metal brittle at low temperatures. Square corners pushed stress beyond what material could handle. The failures were a perfect storm of metallurgical ignorance masked by construction speed that left no room for testing or improvement. Winter 1943 became a furnace testing whether American industrial innovation could overcome its own arrogance. Each failure provided more knowledge about steel behavior under conditions peacetime had never created. Naval architects began grasping that welded construction needed completely different approaches to materials, quality control, and design. Ships shattering in Atlantic storms were conducting the largest metallurgical experiment in maritime history without meaning to. Their destruction was teaching lessons that would reshape materials engineering for generations. Kaiser's revolutionary methods hadn't caused the steel chemistry problems, creating catastrophic failures. They'd simply exposed problems that riveted construction had locked away for centuries. The welding process revealed weakness that had always existed but had been controlled by mechanical joints that stopped cracks from spreading. The crisis wasn't innovation failing, but the painful discovery that old materials couldn't handle new construction techniques. American shipbuilding was paying the most expensive educational bill in industrial history, learning that revolutionary manufacturing demanded equally revolutionary understanding of material science. That education was being purchased with the lives of sailors scattered across the Atlantic floor. The investigation board delivered its final report to the Navy Department in January 1946. Its findings vindicated Henry Kaiser in ways that transformed national thinking about metallurgy and industrial innovation. Of 4,694 welded merchant ships, 970 sustained fractures during the war, a grim number that nonetheless meant over 3,700 vessels successfully carried the supplies that enabled Allied victory. The board's crucial conclusion challenged every assumption about Kaiser's guilt. Welded construction hadn't caused the problems, but had exposed fundamental flaws in ship steel that riveted construction had concealed for centuries. Tipper's metallurgical work provided the scientific proof of Kaiser's innocence. Her crystallographic research showed that the material itself was the true villain. Both welded and riveted ships carried steel with dangerously high sulfur and inadequately low manganese. Riveted construction had masked these problems because mechanical joints acted as crack stoppers. Fractures halted at the boundaries between overlapping plates rather than racing through continuous metal. Welded hulls erased those natural barriers, creating paths where fractures could spread, exposing weakness that had always been buried but had never been tested on this scale. Kaiser's revolution had inadvertently run the largest metallurgical test in maritime history. The engineering answers developed in 1944 proved American industrial capacity could adapt to overcome even catastrophic technical disasters. Naval architects began redesigning Liberty ships by adding riveted crack arresters at key stress points, combining welding speed with mechanical joints' protective qualities. All square corners on windows, doors, and hatches became rounded to eliminate the stress concentrations that had sparked many fractures. Victory ships incorporated these lessons from the start, featuring less rigid designs, better able to absorb fatigue and thermal stress. American industry implemented improvements at its characteristic breakneck pace. New construction standards appeared within months of understanding the problems. Quality control transformed from afterthought into centerpiece. Every welder received additional training focused on preventing the hidden defects that had started failures. X-ray inspection became mandatory for critical seams, finding flaws invisible to the naked eye. Steel chemistry standards changed to guarantee sufficient manganese and lower sulfur. Welding procedures became standardized everywhere, eliminating the inconsistencies that had produced unreliable seams. This systematic approach compressed years of normal development into months driven by wartime pressure. Statistical analysis of Liberty ship performance became undeniable as the war ended. Of 2,710 Liberty ships constructed, only 200 fell to enemy action, a survival rate proving both their structural soundness and their strategic importance in winning the war. The overwhelming majority performed reliably throughout the conflict, transporting millions of tons of supplies across submarine-infested waters. Many served faithfully for decades after the war ended, their welded hulls proving as dependable as traditional riveted construction once steel chemistry issues were fixed. Minor design adjustments and rigorous welding controls implemented in 1947 stopped Liberty ships' structural failures entirely, until 1955, when the last ships were retired. Liberty ship failures shaped material science and structural design far beyond maritime engineering. Systematic examination of how cracks formed and spread evolved into fracture mechanics, fundamentally altering how engineers analyze structures across every industry. Steel manufacturers created alloys with vastly superior resistance to brittle fracture, drawing lessons from analyzing hundreds of failed ship hulls. Welding techniques perfected under wartime pressure became standard worldwide across construction, shipbuilding, and manufacturing. Kaiser's revolutionary methods, refined through painful experience, provided the blueprint for modern industrial production. The global reach of Kaiser's innovations appeared in the decades following victory as former adversaries embraced and improved his mass production approach. Japanese and South Korean shipbuilders absorbed Liberty ship construction methods, incorporating modular assembly and welded techniques into shipyards that would eventually command global maritime manufacturing. The knowledge gained from American structural failures permitted these industries to sidestep similar disasters while achieving production efficiencies exceeding even Kaiser's wartime output. The costly lessons learned during the Atlantic crisis became the foundation for post-war industrial strength that eventually moved from America to Asia. Kaiser's human legacy matched his technical achievements. The healthcare system begun in his shipyards continued serving millions of Americans long after the last Liberty ship launched. Kaiser Permanente, originally established to treat shipyard workers, grew into one of America's major healthcare organizations. The prepaid medical coverage, revolutionary during wartime, became the template for employer health benefits, defining American employment for generations. Kaiser's integration of medical services within industry influenced national healthcare conversations extending into the 21st century. The final recognition of Kaiser's vision emerged not through technical studies but through understanding that his unconventional methods were the only path to the impossible. Traditional shipbuilding, however proven and reliable, couldn't generate vessels quickly enough to replace those sunk by German submarines. At conventional rates, Britain would have fallen to starvation before American production could supply the merchant fleet necessary for Allied success. Kaiser's courage in accepting unknown dangers with welded construction allowed America to build faster than enemies could destroy, converting industrial capacity into the strategic advantage that helped secure victory. The steel plate hoisted by cranes at Richmond Shipyard No. 3 in the war's closing days represented both ending and beginning. Steel, for what would rank among the last Liberty ships, positioned as the previous vessel, touched water beginning her maiden voyage. The production line that seemed impossible in 1941 had become everyday routine by 1945. Its rhythm beat steady as the American industrial pulse. Kaiser had taught his country that sometimes the most perilous path forward was the only route to survival, and that American ingenuity could overcome any technical obstacle when necessity eliminated the privilege of conventional methods. The impossible had become ordinary, one welded seam at a time,